In this session we are going to look at an electrical component called a capacitor, and the circuit symbol for a capacitor can be drawn like this. We can see here these two vertical lines represent the capacitor, and basically in terms of its construction, a capacitor really is just two metal plates separated by an insulating material. So we can show that structure. There we have it then. That's what the construction of a capacitor actually looks like. We've got these two conducting plates, two metal plates, and in between it we have an insulating material that we sometimes call a dielectric. So there we are, an insulating material. And it's important to realise that no charge can actually pass between the two plates of the capacitor because of this insulating material that we have here between them. So really when we charge a capacitor, which we'll have a look at in a moment, all that is really happening is that charge is flowing onto one plate of the capacitor and off the other plate of the capacitor. When a real capacitor is actually constructed, although we've actually got these two parallel plates here, it's important that those plates have as large a surface area as possible, and so to accommodate that, what happens is the plates are actually rolled around a little bit like a Swiss roll with the insulating material sandwiched between them. So here we've got our dielectric material, we've got our two metal plates, two strips of metal foil, and you can see the whole thing is wrapped around. So when you actually get a capacitor, it's got a sort of a cylindrical shape, and that's because of the way it's been constructed here. Yes, you've got these two metal plates, but then they're rolled around like this with an insulating material between them. And there we go. That is basically the construction of the capacitor, but what you need to know is that when we draw it in circuits, that is the circuit symbol that we actually use. So here we actually have a simple electrical circuit which actually involves a capacitor. And what we're going to do is basically connect the capacitor in series with a resistor. What we've actually got here is a 47 microfarad capacitor. So capacitance is measured in farads. We'll have a look at that in a moment. We've got a 47 microfarad capacitor, and we've connected it in series here with a 100 kilo ohm resistor, and then with an ammeter, okay, a microammeter. The current here that's going to flow is going to be pretty small, and then we've also connected a voltmeter across the capacitor. We're going to turn on the power supply, and what we will see here is that a current begins to flow. So a current around about 60 microamps initially flowing in the circuit, and then as time goes on we'll see the current drop, and we'll see the potential difference across the capacitor rise. Now let's try and think about why that is occurring. This circuit diagram then displays the circuit that you've just seen set up. We've got a power supply, positive and negative terminals, DC power supply. We've got a microammeter measuring very small currents. We've got a resistor. We've got our capacitor here. We've got a voltmeter across the capacitor. And what we observed was that as the time went on, the current in the circuit began to drop. The reading across the voltmeter increased. Why was that occurring? Well, first of all, why could a current flow in the circuit? Remember from the construction of the capacitor that between the plates of the capacitor we have an insulating material. Now we know that, we've learnt that we need a complete circuit for a current to flow. So how is it that we have a current at all in the first place? Well, what's actually happening with these very large plates, very large surface area, for a short time a current can actually flow because charge can flow onto one plate of the capacitor and off the other plate of the capacitor. So if we think about our circuit here, positive and negative terminals, conventional current is going to be running here from positive to negative, but we know that a current in a circuit at least is a flow of electrons, which is going from the negative terminal to the positive. So we can imagine here we've got our electrons flowing around our circuit here, and to begin with at least, electrons can move around here, and as the electrons reach this plate here, they start to produce a negative charge on that plate. So this begins to acquire a negative charge, and at the same time electrons are drawn off this plate of the capacitor and move around to the positive terminal. So while the capacitor is charging, while these plates are requiring a charge, a current will actually be seen on our microammeter here. Okay, so on this microammeter we will see a current while electrons are flowing onto one plate and off the other plate of the capacitor. Initially, when the capacitor is uncharged, there will be no volts across the capacitor. reading on the voltmeter will be 0, and all of the volts from the power supply will be across the resistor here, driving a current through that resistor. Because the capacitor and the resistor are in series, potential difference across the capacitor plus the potential difference across the resistor must add up to the terminal PD of the power supply. As the capacitor begins to charge, okay, one plate becomes negatively charged, the other plate becomes positively charged, what we will see then is the potential difference across the capacitor will increase from 0, and we will start to acquire a reading on the voltmeter. And of course that also means the reading on the potential difference across the resistor here would actually be decreasing. And what that means, of course, if we've got less volts across the resistor, less current is going to be passing through the resistor. And you can see why that would really be, because of course as we start to acquire negative charge here on this plate of the capacitor, that is going to repel the incoming electrons. It's going to make it harder now to add more charge to this capacitor. Basically, if you like, we've got the electrical push from the power supply pushing the electrons around this way, but now there's an electrical push here from this capacitor pushing the electrons the other way. And so as we continue to acquire negative charge on that plate and positive charge on that one as the capacitor continues to charge, the potential difference across the capacitor is going to continue to rise, and that's going to cause a continuation of the drop in the current within our circuit, until of course eventually we're going to arrive here with the capacitor fully charged, and at that point then the potential difference across the capacitor will match the EMF of the power supply. There will then be no volts across the resistor at all, and at that point then the current in the circuit will have dropped to 0, and we say, okay, we've fully charged our capacitor. If we were to plot a graph of current against time then for capacitor charging, it would look something like this. Now we'll look more at the nature of this graph and the equations that describe it in a later lesson, but basically you can see here the current is dropping. It basically starts there at T0 with a certain current, it drops away, never quite touches this horizontal axis, it gets closer and closer to it. It drops away fairly quickly with time. Now of course we know that current is rate of flow of charge. The charge equals current multiplied by time. And therefore, as current on the vertical axis, time on the horizontal axis, the area under this graph here would represent the charge that has flowed in our circuit during this time. And of course the charge that flows, if we have a charge Q flow around this circuit, then this plate of the capacitor will acquire a charge of minus Q, this plate of the capacitor will acquire a charge of plus Q. Don't forget, no charge can actually move between the plates of the capacitor, so all the time a current is flowing, one plate is acquiring a negative charge, the other plate a positive charge, an equal positive charge. The size of that charge would be the area under this graph, and the area there would be the charge that has flowed around our circuit, and hence the charge that is stored on our capacitor. So what we could do is we could charge the capacitor up to different voltages. We could, for each charging event, we could plot a graph of current against time, try and determine the area under the graph, and therefore determine the charge. Now if we could get a table of results for the potential difference across the capacitor and the charge stored on the capacitor for different voltages across it, we could investigate the relationship between those two quantities. What would be easier though, rather than having to plot a graph of current against time like this, is if we could somehow keep the charging current constant. Now we could do that if we used here a variable resistor. There we are, we've now made that resistor into a variable resistor. Now what we can do this time is, as the capacitor begins to charge, okay, charge moves around our circuit as an electric current begins to flow, charge starts to acquire on these plates of the capacitor, and we have then an increasing potential difference across the capacitor. We will have a drop in the number of volts across the resistor. If, as the number of volts across the resistor drops, we at the same time reduce the resistance, we could actually keep the charging current constant. Remember, I equals V over R. So okay, for our circuit resistance here, the PD across that resistance will drop, and that normally would cause the current in the circuit to drop, as we can see here. But if, as the PD across the resistor drops, when the PD across the capacitor rises. If as that PD across the resistance drops, we also reduce the resistance. Both values reduce. We can keep this ratio constant. We can have a constant current in the circuit. So what we're going to do, we're going to modify the circuit to do that. And let's have a look at that. So here you can see now we've set up the 100 kilo ohm resistance as a variable resistor. And what we're going to do is we're going to adjust that as the capacitor charges in order to try and maintain a constant charging current. Now that's not easy, but basically here we've got an initial current in our circuit of 62 microamps, and we've measured that earlier. So just short out the capacitor, just see what current would flow through this resistor. So I reckon it's about 62 microamps, and we turn on the power supply then, and what I'm going to do here, just keep reducing the resistance. It's not easy, but sometimes it'll go a bit above, sometimes a bit below, but we're going to maintain an average charging current of 62 microamps all the way through until the capacitor has fully charged. Now if I just time how long it takes to charge the capacitor then with this constant current, at the end of the experiment all I need to do is multiply that current by the time taken for the capacitor to reach each voltage. How long has it taken to reach 1 volt, 2 volts, 3 volts, 4 volts, 5 volts, 6 volts, 7 volts, etc. And once I've got that, then I can multiply the time by the current, get the charge, and I can just plot a graph of charge against potential difference. When we do that and we plot the results, charge against potential difference, what we will find is we get a straight line graph. In other words, the charge stored on a capacitor is directly proportional to the potential difference that is placed across that capacitor. So we can write for a capacitor, the charge stored on it is proportional to the potential difference. Or, if we want, we can write Q equals some constant multiplied by potential difference if they are directly proportional. And that constant is what we call the capacitance. So Q equals CV, where C there is the capacitance, which is measured in farads, symbol capital F. Now that is the formula that defines capacitance. So if we rearrange this, capacitance equals charge divided by potential difference. It is that equation that defines capacitance. Capacitance is the charge that a capacitor will store for each volt you place across that capacitor. Now a farad is an extremely large unit of capacitance, so most capacitors you'll see are in microfarads or even nanofarads. So the capacitor we used, which is a reasonably large one, was 47 microfarads in that last circuit. And what that means is that that capacitor will store 47 microcoulombs of charge if we put 1 volt across its plates. It is important though, when we talk about it storing a charge of 47 microcoulombs, of course, don't forget what that means is one plate is going to get a charge of minus 47 microcoulombs, the other plate will get a charge of plus 47 microcoulombs. That's what we mean when it's stored a charge of 47 microcoulombs. One plate has got a negative charge of that size, and the other plate a positive charge. So here we have a capacitor circuit question. The first part, what quantity is represented by the gradient of the graph? So we've got a capacitor circuit, a 9 volt power supply, a capacitor and a resistor in. And what they've done is they've looked at how the charge stored by the capacitor varies with time. And eventually the charge on the capacitor reaches 300 microcoulombs. What quantity is represented by the gradient of the graph? If we ever get a question like that, really what we want is an equation that relates the two quantities on the y and x axis. Do we know an equation that's going to link charge and time? Well, yeah, we do really, because of course current is rate of flow of charge. So charge, Q, equals I times T. Now, if we look at then the relationship between charge and time, we can compare that to y equals mx plus c. If we plot charge on the vertical axis of a graph and time on the horizontal axis, well, the gradient, the thing that multiplies the x variable, is going to be the gradient, will actually be the current in the circuit. Now that makes sense because of course what's happening to the gradient? Initially it's high, So initially we've got a large current when we first turn on the power supply and the capacitor is uncharged, and we've got all 9 volts across the resistor driving a large current through that resistance. But as the capacitor charges, the PD across the capacitor will increase, the PD across the resistor will decrease. That means less volts across the resistance, means a smaller current through it, and eventually, of course, the gradient reaches 0. We've got a flat line here because the current in the circuit is now 0 once our capacitor is fully charged. So our capacitor there, when fully charged, has a charge on it of 300 microcoulombs. That brings us to the second part then. Okay, so first part here, gradient is equal to the current in the circuit. Yeah, the current drawn from the power supply, or the current going through the resistor here. Find the capacitance of the capacitor. Well, we know that capacitance is charge over potential difference. When the capacitor is fully charged, all 9 volts, because there's going to be no more current in the circuit, so there will be no volts across any of the resistances, all 9 volts will be across the capacitor, and we know at that point we've got 300 microcoulombs. So 300 microcoulombs divided by 9 volts will give us 33.3, if you want, microfarads. So if we keep the current in microcoulombs, then the capacitance will come out in microfarads rather than farads. And there we go. Simple calculation involving capacitance.